There is something you were taught incorrectly about reality, and nobody bothered to tell you. The word is dimension. You hear it and you think of science fiction, parallel worlds, alternate timelines, the mirror universe where everyone has a goatee. Or maybe you think of Einstein and time, some vague association with relativity that you never quite understood, but sounds impressive at dinner parties. None of that is what dimension means. A dimension is simply the number of independent directions you can move. That is all. You can move forward and backward. You can move left and right. You can move up and down. 3 directions. 3 dimensions. If there were a 4th direction, perpendicular to all 3 of those, you could not point toward it. You could not imagine it. Your brain literally lacks the neural architecture to visualize it. But that does not mean it cannot exist. And here is what nobody tells you. Mathematicians have been working in 4 dimensions, 5 dimensions, 10 dimensions, 100 dimensions, infinite dimensions for over 170 years, not speculating, not theorizing, working, proving theorems, calculating properties. The mathematics of higher dimensional space is as rigorously established as the Pythagorean theorem. It is not a question of whether higher dimensional geometry is logically coherent. That was settled before the American Civil War. The question, the one that has consumed a century of physics and tens of billions of dollars in experimental equipment, is whether you are living inside one of these structures right now, whether our physical universe actually contains dimensions you cannot perceive. And that question remains violently, stubbornly, disturbingly open. There is a story about a creature who discovered the truth about the shape of his reality. He was a square. He lived in a 2-dimensional world called Flatland. One day, a sphere visited him from the 3rd dimension. The sphere lifted the square bodily out of his flat world and showed him what reality actually looked like from above. The square saw his own house from a perspective that should have been impossible. He understood, for the first time, that his entire existence had been confined to a plane, that there was a direction called up that he had never been able to point toward or even properly conceive. He returned to Flatland and preached what he had seen. He called it the Gospel of 3 dimensions. His own brother reported him to the authorities. He was declared a heretic. He was imprisoned. He wrote his account from a cell. His name was A Square. His testimony is 140 years old. And what happened to him may be happening to us. The book was published in 1884 under the pseudonym A Square. The author was Edwin Abbott Abbott. And yes, that is his real name, the double surname inherited from parents who were first cousins. Abbott was not a mathematician. He was a schoolmaster, headmaster of the City of London School at the remarkably young age of 26, an Anglican priest, a Shakespeare scholar, the author of more than 50 works on theology and grammar. Among his students was the future British Prime Minister H. Asquith, who credited Abbott as the teacher to whom he owed the deepest obligation. Abbott died in 1926 of influenza. His obituary in the Times, lengthy and respectful, fails to mention Flatland. The original Dictionary of National Biography entry likewise omits it. The only work for which Abbott is remembered was considered, in his lifetime, a minor curiosity, a mathematical joke, a satirical oddity that sold poorly in its first edition. But the book itself is devastating. The first half is savage Victorian satire. Flatland is a two-dimensional world where your social class is determined by your shape. Women are straight lines, nearly invisible from certain angles, lethally sharp if approached wrong. They are required to emit a peace cry in public to prevent accidental impalings. In some provinces, they are forbidden from leaving their homes entirely. They are considered intellectually inferior, emotionally unstable, dangerous by nature. This is not science fiction. This is Victorian England, with the subtext made geometric. Soldiers are narrow isosceles triangles. The middle class are equilateral triangles. Professionals are squares and pentagons. Nobility are hexagons with increasing numbers of sides. The priestly elite are circles, or rather polygons with so many sides they appear circular. Abbott was not writing whimsy. He was attacking Victorian class rigidity, gender oppression, and phrenology, the pseudoscience that held that the shape of your skull determined your intelligence. In Flatland, the equation is literal. More sides equals more status. A square is smarter than a triangle. By geometric definition, the ruling circles enforce this hierarchy with brutal precision. Any irregular polygon, any shape that deviates from perfect symmetry, is either killed at birth or permanently confined to a lower caste. The satire is biting. The circles have convinced the population that this geometric hierarchy is natural, divinely ordained, scientifically obvious. Anyone who questions it is suppressed. The phrase sounds like nothing more than a children's geometry lesson. But Abbott was describing his own society. The second half delivers the mathematical payload. The narrator, A Square, first dreams of Lineland, a one-dimensional world. The king of Lineland is the longest line segment. He knows only forward and backward. His subjects are shorter lines arranged along the single axis of existence. A square tries to explain a second dimension, tries to describe what left and right mean to a creature who knows only forward and backward. He utterly fails. The king cannot conceive of a direction perpendicular to his single line of existence. He cannot imagine stepping outside the line. The very concept is meaningless to him. He dismisses A Square as a madman. This failure is deliberate. Abbott is preparing the reader. Then, a three-dimensional sphere visits Flatland. What a square perceives is this: a point appears from nowhere. It grows into a circle. The circle reaches its maximum diameter, then shrinks. It becomes a point again. It vanishes. What has actually happened is that a sphere has passed through the two-dimensional plane of Flatland. A square has witnessed the cross-sections, the slices of a three-dimensional object as it moves through a two-dimensional world. He has no framework to understand what he is seeing. The sphere is not a circle. It is something else entirely, something that extends in a direction A Square cannot point toward. The sphere tries to explain. Imagine, it says, a point. Move that point in one direction and it sweeps out a line. Move that line perpendicular to itself and it sweeps out a square. Move that square perpendicular to itself in a direction that does not exist in the square's plane, and it sweeps out a cube. A square finds this reasoning interesting but unconvincing. Mathematics is one thing. Reality is another. You are asking me to believe in a direction I cannot see, cannot imagine, cannot point toward. So the sphere lifts A Square out of Flatland entirely. The passage is extraordinary. A square feels himself rising. He feels a sensation he has never experienced, movement in a direction that should not exist. And then he sees Flatland from above. For the first time in his existence, A Square sees his world as it actually is. He sees the insides of houses, the closed chambers that should be hidden from any Flatlander's view. He sees the interiors of his fellow citizens, their internal organs visible from this impossible vantage point. He sees his own house, his own family, from a perspective that is literally unimaginable from within the plane. He understands, with a force that the book describes as almost religious, that his entire model of reality was incomplete. There was always a direction he could not point toward, a direction called up, and he had been as blind to it as the king of Lineland was blind to left and right. The sphere returns A Square to Flatland, and A Square begins to preach. He calls it the gospel of 3 dimensions. He tells anyone who will listen that their understanding of reality is fundamentally wrong, that there is a 3rd dimension, that he has seen it directly, that the circles are lying to them about the nature of existence. His brother reports him to the authorities. He is tried. He is convicted of heresy. The same society that enforces geometric hierarchy now enforces geometric cosmology. There is no 3rd dimension. There cannot be. Anyone who claims otherwise is a threat to the social order. He is imprisoned, and from his cell he writes, not because anyone will believe him, but because he has seen what he has seen. Abbott was not the first to think about dimensions this way. The tradition stretches back further than you might expect. In 1846, nearly 40 years before Flatland, the German physicist Gustav Theodor Fechner published a short essay under the pseudonym Dr. Mises. It was called Space Has 4 Dimensions. Fechner imagined a shadow man projected on a screen, able to interact with other shadows, but utterly incapable of conceiving a direction perpendicular to the screen. The shadow man invents forces to explain the movements of other shadows. He cannot imagine that there is a world beyond the screen from which those movements originate. Fechner's argument was simple. Just as creatures living in 2 dimensions could not conceive a 3rd, so we creatures of the 3rd dimension cannot conceive a 4th. Our limitation is not logical impossibility. It is perceptual blindness. Even earlier, Plato's allegory of the cave made a similar point. Prisoners chained in a cave see only shadows on the wall. They mistake the shadows for reality. One prisoner escapes, sees the actual world, returns to describe it, and is not believed. The pattern repeats. Someone sees beyond the limitations of their world. They try to communicate what they have seen. They are dismissed or destroyed. The man who gave us the word for a 4-dimensional cube was a bigamist who died after toasting female philosophers. Charles Howard Hinton was born in 1853, the son of James Hinton, a surgeon and radical advocate of polygamy, who declared that Christ was the savior of men, but he himself was the savior of women. The elder Hinton's philosophy was that men should be permitted multiple wives. His son would put this philosophy into practice with disastrous results. Charles studied at Oxford, married Mary Ellen Boole, daughter of the George Boole of Boolean logic, and taught mathematics at Uppingham School alongside a man named Howard Candler. It was to H.C. that Abbott dedicated Flatland. The circles of Victorian intellectual life were small. In 1883, Hinton secretly married a second woman, Maud Florence Weldon, under the false name John Weldon. They had twin sons. The bigamy was not immediately discovered. Hinton lived a double life for 3 years. In 1886, he confessed, or perhaps was discovered. The accounts vary. What is certain is that he was tried and convicted of bigamy at the Old Bailey and served 3 days in prison. His academic career in England was over. He fled to Japan with his first wife, became headmaster of a school in Yokohama, and eventually moved to Princeton University in 1893. At Princeton, Hinton invented a gunpowder-powered baseball pitching machine that hurled balls at 70 miles per hour. The machine was eventually abandoned, according to contemporary accounts, by the players in fear of their lives. Hinton was fascinated by mechanical devices and wrote science fiction stories involving characters who could access the fourth dimension. Hinton coined the word Tesseract in 1888 in his book A New Era of Thought. It comes from the Greek tessara, meaning four, and actis, meaning ray, describing the four edges that radiate from each vertex of a four-dimensional cube. He invented what he called Hinton cubes, colored wooden blocks meant to train the mind to visualize four-dimensional space. The system was elaborate, requiring users to memorize colors and spatial relationships through years of practice. Rumors circulated that the system had driven more than one person insane. This may have been exaggeration. It may not have been. On April 30th, 1907, Hinton attended a meeting of the Washington Philosophical Society. He offered a toast to female philosophers. He then walked to the lobby and collapsed. Cerebral hemorrhage. He was 54 years old. 1 year later, his first wife, Mary Ellen, committed suicide in Washington. The man who named the fourth dimension lived a life that seemed to prove dimensions could break a person. The Tesseract is not a metaphor. It is not a visualization trick. It is a mathematical object with precisely defined properties, as rigorously characterized as any triangle or sphere. A point has 0 dimensions. It is a location, nothing more. It has no length, no width, no height. It is a position in space, without extension. Move a point in one direction and you sweep out a line. A line has 2 endpoints, 1 dimension. You need 1 number to specify a position on the line. Move a line perpendicular to itself and you sweep out a square. A square has 4 vertices and 4 edges. 2 dimensions. You need 2 numbers to specify a position on the square. Move a square perpendicular to itself in a direction that does not exist in the square's plane, and you sweep out a cube. A cube has 8 vertices, 12 edges, and 6 square faces. 3 dimensions. You need 3 numbers to specify a position in the cube. Move a cube perpendicular to itself in a direction that does not exist in 3-dimensional space, and you sweep out a tesseract. A tesseract has 16 vertices. It has 32 edges. It has 24 square faces. It has 8 cubical cells. These numbers are not arbitrary. They follow from the same geometric logic that tells you a cube has 8 vertices. Each vertex of a tesseract is connected to 4 edges, just as each vertex of a cube is connected to 3 edges. Each edge of a tesseract is bounded by 2 vertices, just as each edge of a cube is bounded by 2 vertices. The combinatorics are exact. You can prove them. You can calculate them from first principles. The tesseract is as precisely defined as a triangle. When projected from 4 dimensions into 3, the tesseract produces an iconic image, a cube within a cube. The inner cube is connected to the outer cube by 6 frustum-shaped cells that look distorted but are actually undistorted cubes seen from a 4-dimensional angle. This is exactly analogous to how a wireframe cube, when drawn on a 2-dimensional page, appears as a small square inside a large square, connected by 4 trapezoidal regions that are actually undistorted squares seen in perspective. During a 4-dimensional rotation, which occurs around a plane rather than an axis, the inner cube appears to swell outward while the outer cube shrinks inward. They seem to pass through each other and swap positions. The breathing, pulsing motion is hypnotic and deeply strange, but it is purely a projection artifact. In 4 dimensions, all 8 cubes remain perfectly regular and never interpenetrate. They are not distorted, they are not moving through each other. Our 3-dimensional perception is simply inadequate to represent what is actually happening. If a tesseract passed through our 3-dimensional space face first, we would see a cube materialize from nothing, persist for a moment, and vanish. If it passed through corner first, we would see a point grow into a tetrahedron, morph through increasingly complex polyhedra, reach a maximum cross-section, then reverse and disappear. We would have no way of understanding what we were seeing unless someone told us about the 4th dimension. Salvador Dali spent a decade obsessed with the 4th dimension. In 1954, he painted Crucifixion, subtitled Corpus Hypercubus, oil on canvas, 194.3 centimeters by 123.8 centimeters. It hangs in the Metropolitan Museum of Art, Gallery 901, a gift of Chester Dale in 1955. The painting depicts Christ floating before a cross made from the unfolded net of a tesseract, 8 cubes arranged in a 3-dimensional crucifix. Christ's body bears no wounds, no nails, no crown of thorns. He hovers in front of the hypercube cross rather than being affixed to it. Below, Gala, Dali's wife, appears as Mary Magdalene, gazing upward from a checkerboard floor that extends to infinity. Dali had published his mystical manifesto in 1951. He proclaimed a new synthesis of Catholicism, mathematics, and modern science that he called nuclear mysticism. The unfolded hypercube represents transcendence. Just as a 2-dimensional net is the flattened representation of an incomprehensible 3-dimensional cube, so the 3-dimensional cross is the shadow of an incomprehensible 4-dimensional tesseract. And Christ, in Dali's theology, is the manifestation of incomprehensible divine truth in comprehensible human form. Thomas Banchoff, a geometer at Brown University, had been creating computer visualizations of 4-dimensional objects since 1967. He was a pioneer in using early computer graphics to display projections of the tesseract and other polytopes. In 1975, he received a phone call summoning him to meet Salvador Dali. He assumed it was either a hoax or a lawsuit. At their first meeting, Dali declared Banchoff the ambassador from mathematics land. When shown Banchoff's folding hypercube model, Dali said simply, "I may have this." It was not a question. The model now resides permanently in the Dali Museum in Figueres, Spain. They collaborated for over a decade, Dali was genuinely interested in the mathematics, not just the aesthetic possibilities. He wanted to understand what he was painting. Banchoff found him to be a serious student, if an eccentric one. Dali once told Banchoff that thinkers and literati could give him nothing. Scientists give me everything, even the immortality of the soul. You might think all of this is mathematical abstraction. Beautiful games with symbols, geometry that exists in equations, but not in the physical world. That would be comforting. But if higher dimensions were just games, physics would not care about them. And physics cares very much. On October 16, 1843, William Rowan Hamilton was walking along the Royal Canal in Dublin with his wife. He had been struggling for years with a problem. He could add and subtract three-dimensional quantities, but he could not multiply them. His children had taken to asking him every morning at breakfast, "Well, Papa, can you multiply triplets?" And every morning he would reply with a sad shake of the head, "No, I can only add and subtract them." On that Monday, something happened. In Hamilton's own words, an electric circuit seemed to close. He suddenly saw how to do it. The formula required 4 components, not 3, and it required sacrificing a property called commutativity, the property that says A times B equals B times A. In Hamilton's system, that was no longer true. I times J equaled K, but J times I equaled negative K. He was so excited that he carved the formula into the stone of Brogan Bridge. I squared equals J squared equals K squared equals IJK equals -1. The plaque on the bridge was unveiled in 1958 by Eamon de Valera, who had been a lifelong quaternion enthusiast. Every year, mathematicians make pilgrimages to the bridge to commemorate the discovery. Hamilton had proven that meaningful algebra could exist in 4 dimensions. He had to pay a price. Multiplication no longer worked the way it did with ordinary numbers, but the mathematics was consistent. The mathematics worked. In 1844, Hermann Grassmann published Die Lineal-Ausdehnungslehre, the theory of linear extension. He had invented, essentially, linear algebra, vector spaces of arbitrary dimension, the mathematical framework that would eventually underpin everything from quantum mechanics to machine learning to the algorithm that decides what you see on social media. His reward was near total obscurity. Mobius called the book unreadable. Balzer said it made him feel dizzy and to see sky blue before his eyes. Hamilton, who should have recognized a kindred spirit, could not make sense of it. The mathematical community ignored Grassmann's work almost entirely. Some 600 copies remained unsold by 1864, 20 years after publication. Grassmann gave up on mathematics. He turned to Sanskrit. He produced a celebrated translation of the Rig Veda that is still consulted by scholars. He died in 1877, recognized as a linguist, not a mathematician. Freeman Dyson wrote in 1972, "With the advantage of hindsight, we can see that Grassmann's was the greater contribution to mathematics than Hamilton's. His work is now recognized as foundational to modern algebra, differential geometry, and theoretical physics. But Grassmann never knew this. His own epitaph reads, 'I remain completely confident that the labor I have expended will not be lost.' He was right, but he did not live to see it. Ludwig Schlafly, working between 1850 and 1852, classified all regular polytopes in every dimension. This is the generalization of the Platonic solids to higher dimensions. In 2 dimensions, there are infinitely many regular polygons, equilateral triangles, squares, regular pentagons, hexagons, and so on without end. In 3 dimensions, there are exactly 5 regular polyhedra, the tetrahedron, cube, octahedron, dodecahedron, and icosahedron. Plato associated each with one of the classical elements. These are the Platonic solids. In 4 dimensions, Schlafly proved there are exactly 6 regular polytopes, the 4-dimensional simplex with 5 tetrahedral cells, the Tesseract with 8 cubical cells, the 16 cell with 16 tetrahedral cells, the 24 cell with 24 octahedral cells, a polytope with no 3-dimensional analog, the 120 cell with 120 dodecahedral cells, and the 600 cell with 600 tetrahedral cells. In 5 dimensions and higher, there are exactly 3 regular polytopes in every dimension: the simplex, the hypercube, and the cross polytope. These are proven facts. Schlafly demonstrated them with mathematical rigor. His masterwork, Theorie der vielfachen Kontinuität, was rejected by the Austrian Academy for being too long. It was rejected by the Berlin Academy without explanation. No journal would publish it. The complete work finally appeared in print in 1901. Schlafly died in 1895, 6 years before his masterwork was published. On June 10, 1854, a shy, nervous young mathematician named Bernhard Riemann delivered his habilitation lecture at the University of Göttingen. This was the final requirement for the right to teach at a German university. The candidate submitted 3 possible lecture topics, and the examining committee chose 1. Carl Friedrich Gauss, the greatest mathematician of the age and the chairman of the examining committee, deliberately picked the topic Riemann was least prepared for. On the hypotheses which lie at the foundations of geometry. Riemann was terrified. He had not fully developed his ideas on this subject, but he had no choice. The lecture changed mathematics. Riemann argued that there was, in his words, a certain darkness at the foundations of geometry. The axioms of Euclid were not self-evident truths about the universe. They were assumptions, and different assumptions could lead to different geometries, all equally valid mathematically. He then built a framework for geometry in any number of dimensions. He showed how to define distance and curvature in spaces with n coordinates. He demonstrated that space itself could be curved, with that curvature measurable from within the space, without reference to any external vantage point. A 2-dimensional creature living on the surface of a sphere could, through careful measurement, detect that its space was curved, even without being able to see the sphere from the outside. The lecture contained almost no formulas. The audience included the entire philosophy faculty, and Riemann knew they would not follow technical mathematics. He conveyed the ideas in words and geometric intuitions. Gauss understood. After the lecture, Gauss spoke to his colleague Wilhelm Weber with the greatest praise and rare enthusiasm about the depth of the thoughts that Riemann had presented. Among the audience, only Gauss fully appreciated what had just happened. The lecture was not published until 1868. Riemann had died of tuberculosis 2 years earlier, on the shores of Lake Maggiore in Italy. He was 39 years old. He had fled to Italy, hoping the warmer climate would help his failing lungs. It did not. His housekeeper reportedly discarded unpublished manuscripts while tidying his effects. 60 years later, Einstein's general theory of relativity would vindicate Riemann's framework completely. The curvature of space-time, the bending of space by mass and energy, the geometry of black holes and gravitational waves, all of it was built on the mathematics Riemann presented to an audience that mostly did not understand him, in a lecture that was not published until after his death. By 1911, a bibliography of works on n-dimensional geometry listed 1832 references. The field Riemann had opened became a torrent. You might say, fine, the mathematics is proven. Higher dimensional spaces are logically consistent, but that does not mean they physically exist. A theorem about 10-dimensional space does not mean our universe has 10 dimensions. That would be reasonable. But then you would have to explain why the only known consistent theory of quantum gravity refuses to work in any number of dimensions other than 10. In April 1919, a German mathematician named Theodor Kaluza wrote a letter to Albert Einstein. Kaluza had noticed something remarkable. If you solve the equations of general relativity in 5 dimensions instead of 4, you do not just get gravity, you get electromagnetism as well. Maxwell's equations, the laws governing electric and magnetic fields, emerge automatically from the geometry of the extra dimension. Einstein's response was electric. I like your ideas enormously. The formal unity of your theory is startling. Then Einstein sat on the paper for 2 years. The problem was simple. Is the 5th dimension real, or is it a mathematical trick? Einstein could not decide. On September 14th, 1921, he wrote to Kaluza admitting that it might have been a mistake not to submit the paper earlier. He finally communicated it for publication on December 8th, 1921, more than 2 years after he first received it. Kaluza himself described his theory as possessing virtually unsurpassed formal unity, which could not amount to the mere alluring play of a capricious accident. The mathematics was too beautiful to be coincidence. But was it physics? Kaluza was a remarkable man. He studied more than 15 languages. His favorite was reportedly Arabic. He never used lecture notes, except once, to copy down a 50-digit number. And most famously, being a non-swimmer, well past the age of 30, he once read a book on swimming, walked to a river, jumped in, and swam successfully on his first attempt. His son confirmed this was done deliberately to demonstrate the much-abused practicality of theoretical knowledge. In 1926, the Swedish physicist Oskar Klein independently developed a 5-dimensional theory and added a crucial insight. The reason we do not perceive the 5th dimension is that it is curled up into a tiny circle, approximately 23 times the Planck length, roughly 10 to the negative 30th centimeters, far too small to detect. The extra dimension is there, but it is compact, rolled up, hidden at every point in space. Think of a garden hose. From far away, it looks like a one-dimensional line, but up close, you can see that it has a circular cross-section. A tiny ant could walk around the circumference of the hose at any point along its length. Similarly, at every point in our 3-dimensional space, there might be an additional circular dimension, curled up so small that no experiment we can currently perform would detect it. This is the Kaluza-Klein theory. It was the first serious proposal that extra dimensions could be physically real and experimentally invisible. It unified gravity and electromagnetism, through pure geometry, and it was ignored by mainstream physics for decades, dismissed as a mathematical curiosity with no physical meaning. History has a way of vindicating the ignored. In 1968, a young physicist named Gabriele Veneziano at CERN was studying the strong nuclear force, the force that holds protons and neutrons together. He discovered that a 240-year-old mathematical formula, the Euler beta function, could describe hadron scattering amplitudes with uncanny accuracy. Particles collided, scattered, and the probabilities matched this ancient formula. He had no idea why. In 1969 and 1970, 3 physicists independently provided the explanation. Yoichiro Nambu in Chicago, Holger Becht-Nielsen in Copenhagen, and Leonard Susskind at Stanford all realized that Veneziano's formula emerges naturally if you model particles not as points, but as tiny, vibrating, one-dimensional strings. String theory was born, and almost immediately it developed a problem. In December 1970, a British physicist named Claude Lovelace gave a talk at a seminar in Princeton. Lovelace was eccentric even by physicist standards. He never completed his PhD. He had taught himself physics at age 15 in South Africa. He had been working on the consistency conditions of string theory, and he had found something strange. The theory only worked in 26 dimensions, specifically the mathematical anomalies that plagued the theory. The inconsistencies that made its predictions nonsensical vanished precisely when space-time had 26 dimensions, not 25, not 27, 26. Lovelace recalled that his talk got a bad reception. I used the 26 dimensions as a joke, and it indeed produced laughter. He published the result in Physics Letters B in March 1971, burying it near the end of the paper because he thought it was embarrassing. John Schwartz, who would later become one of the architects of superstring theory, remembered the shock. Lovelace's paper was quite a shock to everyone, since until then, nobody considered allowing the dimension of space-time to be anything but 4. We were doing hadron physics after all, and 4 was certainly the right answer. When supersymmetry was incorporated into string theory, something remarkable happened. The critical dimension dropped from 26 to 10. This is not a choice. This is not a model assumption. This is a mathematical requirement, as rigid as the requirement that 2 plus 2 equals 4. A vibrating string sweeps out a 2-dimensional surface called a world sheet. For the quantum theory on this world sheet to be consistent, it must possess a symmetry called conformal invariance. But quantizing the theory introduces anomalies that threaten to destroy this symmetry. The anomaly is characterized by a number called the central charge. Each dimension of space-time contributes to this central charge. Ghost fields from the gauge fixing procedure contribute a negative amount. For the anomaly to cancel exactly, the contributions must sum to 0. For bosonic strings, this happens when there are 26 dimensions. For superstrings, which include fermions and supersymmetry, this happens when there are 10 dimensions. There is no wiggle room. You cannot have 9 dimensions or 11 dimensions and still have a consistent theory. The mathematics does not permit it. If you insist on fewer dimensions, you must either abandon Lorentz invariance, the symmetry at the heart of special relativity, or abandon conformal invariance on the world sheet, which makes the theory physically meaningless. Neither option is acceptable. The requirement is as non-negotiable as the requirement that 2 plus 2 equals 4. You might ask, why should I care what string theory requires? Maybe string theory is wrong. That is a fair question, but you should know what you are dismissing. String theory is the only known consistent theory of quantum gravity. It is the only framework that successfully combines Einstein's general relativity with quantum mechanics without producing infinities that make the theory meaningless. Every other approach to quantum gravity has failed at some level. Loop quantum gravity struggles with the classical limit. Asymptotic safety lacks proof of existence. Causal dynamical triangulations have limited applicability. String theory has passed every mathematical consistency check thrown at it. More than that, string theory has produced extraordinary mathematics. Edward Witten won the Fields Medal in 1990, the highest honor in mathematics, for work that emerged directly from string theory. He was the first physicist ever to receive the award. The citation praised his command of mathematics, rivaled by few mathematicians. String theory has connections to number theory, to topology, to algebraic geometry, to representation theory. It has solved problems in pure mathematics that had resisted solution for decades. It has revealed unexpected connections between physical theories that seemed completely unrelated. Whatever else it is, string theory is not arbitrary. It is not a collection of ad hoc assumptions. It has a mathematical depth and coherence that commands respect even from its critics. And this theory, this mathematically profound and uniquely consistent theory, absolutely requires that space-time has 10 dimensions. In 1974, two physicists named Joel Shirk and John Schwartz made a paradigm-shifting proposal. String theory had been developed to describe the strong nuclear force, but it contained a massless spin 2 particle that had no place in hadron physics. Most physicists considered this an embarrassment, a sign that the theory was wrong about the strong force. Shirk and Schwartz proposed that the embarrassment was actually a graviton. The theory was not about hadrons at all. It was about quantum gravity. Almost nobody listened. Quantum chromodynamics had just emerged as the correct theory of the strong force. The physics community had moved on. String theory was yesterday's failed model. For the next decade, string theory entered what Schwartz later called the wilderness years. The physics community had abandoned it. Funding dried up. Career paths closed. Schwartz continued working on it at Caltech, not as faculty, but as a research associate, sustained only by the patronage of Murray Gell-Mann, who believed the mathematics was too beautiful to be meaningless. Joel Shirk did not survive the wilderness. On May 16, 1980, Shirk died in Paris. He was 33 years old. The reported cause was a diabetic coma. He had been found without access to insulin. His personal life had deteriorated. He had struggled with depression and isolation. He never lived to see string theory vindicated. John Schwartz later wrote, "It is a pity that he could not participate in these developments and enjoy the recognition that he deserved." In August 1984, at a workshop in Aspen, Colorado, Michael Green and John Schwartz completed a calculation that changed everything. They showed that the gauge anomalies in type 1 superstring theory, the inconsistencies that had seemed fatal, cancel exactly if the gauge group is SO32 or E8 times E8. Both groups have dimension 496. Green later recalled the moment of completion. It was a stormy night in Aspen. There was lightning outside, and when they found 496 on each side of the equation, Breen said, "The gods are trying to prevent us from completing this calculation." They succeeded anyway. Edward Witten's response appeared almost immediately. In a stunning development, he wrote, "Within months, hundreds of physicists pivoted to string theory. The field went from a backwater to a flood. The first superstring revolution had begun. By 1985, 5 consistent superstring theories had been identified: Type 1, Type 1IA, Type YIB, heterotic SO32, and heterotic E8 times E8. All of them required 10 dimensions. All of them incorporated gravity automatically. All of them were mathematically consistent. The question was no longer whether string theory worked. The question was which version was correct and how the extra dimensions were hidden. In 1995, at the Strings Conference at the University of Southern California, Edward Witten announced that the 5 known consistent superstring theories were not separate theories at all. They were different limiting cases of a single underlying framework in 11 dimensions. He called it M theory. The M could stand for master, or mathematical, or mother, or mystery, or membrane, or magic, or matrix. Witten reluctantly admitted that it could also stand for murky, because the level of understanding of the theory was so primitive. M theory unified the superstrings. It explained their relationships. It suggested that the fundamental objects of the theory were not just strings, but also higher dimensional membranes, called branes. It launched the second superstring revolution. And it required 11 dimensions. Edward Witten himself is one of the most remarkable figures in modern physics. He earned a bachelor's degree in history from Brandeis in 1971 with a minor in linguistics. He wrote for The Nation and The New Republic. He worked on George McGovern's presidential campaign in 1972. He enrolled in graduate economics at Wisconsin and quit. He tried applied mathematics at Princeton and quit. Then he pivoted to physics, earning his PhD in just 3 years, under David Gross. He became the first physicist to win the Fields Medal in 1990. Michael Atiyah's citation said that, although he is definitely a physicist, his command of mathematics is rivaled by few mathematicians. Some physicists joke, with only partial humor, that Witten is not a human being, but an alien sent to help us understand the universe. He unified 5 theories into one. He proposed that the true theory lives in 11 dimensions, and he admitted that we do not fully understand what we have found. Here is what we know. The mathematics of higher dimensional spaces is proven. It has been proven for over 170 years. The Tesseract, the Calabi-Yau manifold, the structure of 10-dimensional spacetime, these are not speculations. They are theorems. String theory requires 10 dimensions. M theory requires 11 dimensions. These requirements are as mathematically rigid as the requirement that 2 + 2 = 4. These are the only known consistent theories of quantum gravity. And for over a century, physicists have been searching for experimental evidence that extra dimensions exist. The Large Hadron Collider at CERN is the most powerful particle accelerator ever built. It collides protons at energies up to 13.6 tera electron volts. more than 10,000 times the energy released by a mosquito in flight, concentrated into a space smaller than an atomic nucleus. It has searched for signs of extra dimensions in multiple ways. Graviton emission would appear as events with missing energy, where particles seem to disappear into the extra dimensions. Virtual graviton exchange would modify the distribution of particles in predictable ways. Microscopic black holes could form if extra dimensions exist at the TeV scale. Kaluza-Klein graviton resonances, heavier copies of particles carrying momentum in the extra dimensions, would appear as bumps in mass distributions. The results from ATLAS and CMS through Run 2, representing 140 inverse femtobarns of data, are as follows. ADD model, fundamental Planck scale, for 2 extra dimensions, excluded below approximately 11 tera-electron-volts. Randall-Sundrum Kaluza-Klein graviton mass, excluded below approximately 4.8 tera-electron-volts. Microscopic black hole thresholds, excluded up to approximately 10 tera-electron-volts. No extra-dimensional signatures have been observed. Tabletop gravity experiments at the University of Washington, using exquisitely sensitive torsion pendulums, have verified Newton's inverse square law down to separations of 52 micrometers. If extra dimensions were large enough to modify gravity at these scales, the experiments would have detected them. No deviations found. Astrophysical constraints from supernova SN 1987A and from neutron star heating push the bounds even further. If extra dimensions existed at detectable scales, supernovae would lose energy into them. Neutron stars would cool or heat in anomalous ways. The observations constrain the ADD model fundamental Planck scale to be greater than approximately 1700 tera-electron-volts for 2 extra dimensions, and the radius of the extra dimensions to be less than 0.16 nanometers, far beyond the reach of any experiment we can currently build. The parameter space for detectable extra dimensions shrinks with every null result. The dimensions, if they exist, must be smaller. The energy scales, if they are relevant, must be higher. The experimental silence grows louder. Richard Feynman, in a 1987 interview, was asked about string theory. His response was characteristically blunt. "I do feel strongly that this is nonsense. I don't like it that they're not calculating anything. All these numbers, the masses of particles, the charges, the coupling constants, have no explanations in these string theories. Absolutely none. I don't like that for anything that disagrees with an experiment, they cook up an explanation, a fix-up, to say, well, it might be true. For example, the theory requires 10 dimensions. Yes, that's possible mathematically, but why not 7? He concluded, "I think all this superstring stuff is crazy and is in the wrong direction." Feynman died in 1988. He never saw what came next. Sheldon Glashow won the Nobel Prize in 1979 for his work on electroweak unification. He has spent decades publicly campaigning against string theory. In a 1986 article in Physics Today, co-authored with Paul Ginsparg, he warned that contemplation of superstrings may evolve into an activity to be conducted at schools of divinity by future equivalents of medieval theologians. In a PBS documentary, The Elegant Universe, he called string theory a tumor. He has stated bluntly that there are physicists and there are string theorists, and that string theorists in general will not attend lectures on experimental physics. According to multiple accounts, Glashow left Harvard partly because the physics department had become dominated by string theorists he had unsuccessfully campaigned against hiring. A Nobel laureate, driven from his own institution, over a theory that makes no testable predictions. The divide in physics is real and bitter. At conferences, string theorists and their critics barely speak to each other. Hiring decisions at major universities have become proxy wars between factions. Graduate students are warned about which thesis advisors will help or hurt their careers, depending on which side of the debate they land. Lee Smolin, in his 2006 book The Trouble with Physics, documented what he called the sociology of string theory. The field, he argued, had become an echo chamber. Papers were cited only if they supported the dominant paradigm. Alternative approaches to quantum gravity were starved of funding and attention. Young physicists who questioned string theory found their careers stalled. The one option that never comes up, Smolin wrote, is that the theory might simply be wrong. Peter Voigt, a mathematician at Columbia, maintains a blog called Not Even Wrong that has become the central clearinghouse for string theory criticism. The title comes from Wolfgang Pauli's famous dismissal of a particularly poor physics paper. Not only is it not right, Pauli said, it is not even wrong, meaning the theory was so vague, so untestable, that it did not rise to the level of being falsifiable. White argues that string theory has reached this state. The landscape of 10 to the 500th vacua is not a prediction. It is an admission of failure. If your theory is compatible with any possible universe, then it predicts nothing about our universe. If it predicts nothing, then it explains nothing. If it explains nothing, then it is not science. The defenders of string theory push back. David Gross, a Nobel laureate and string theorist, argues that the theory is still in its early stages. We do not yet fully understand it. Perhaps when we do, the landscape problem will resolve itself. Perhaps there is a selection mechanism we have not discovered. Perhaps the mathematics will eventually tell us which vacuum is ours. Witten himself maintains a studied neutrality in public, declining to engage with the critics directly. When pressed, he notes that string theory is the only game in town for quantum gravity. Every alternative has failed. String theory has not. That is worth something, even if we cannot yet make experimental predictions. The argument continues. Neither side concedes, and the experiments return null results, year after year, pushing the possible extra dimensions into ever smaller corners of parameter space, tightening the noose without ever closing it completely. The landscape problem makes everything worse. In 2000, Raphael Bousseau and Joseph Polchinski estimated that string theory admits approximately 10 to the 500th power distinct vacuum configurations. Each configuration corresponds to a different way of compactifying the extra dimensions, decorated with quantized magnetic fluxes. Each one produces different particle physics, different force strengths, different cosmological constants, different laws of nature. More recent estimates using F-theory compactifications suggest the number may exceed 10 to the 272,000th power. Each vacuum is a different possible universe, and string theory provides no mechanism for selecting among them, no way to predict which one we inhabit, no way to test which configuration is correct. Some physicists, like Leonard Susskind, argue that this landscape, combined with eternal inflation, provides an anthropic explanation for the cosmological constant. We observe the universe we observe because it is one of the rare vacua compatible with observers. The other 10 to the 500th universes exist, but they contain no one to observe them. Critics call this the abandonment of science. If a theory predicts everything, it predicts nothing. If any outcome is compatible with the theory, then the theory is unfalsifiable. Joseph Polchinski himself admitted that the vacua are jury-rigged, Rube Goldberg contraptions that could hardly have fundamental significance. And yet, the mathematics still works. String theory still combines gravity and quantum mechanics consistently. The requirement for 10 dimensions still holds as rigidly as it did in 1970. A century of null results does not disprove a theory. It constrains the parameter space. The extra dimensions, if they exist, must be smaller than we can probe. The energy scale must be higher than we can reach. But nothing in the mathematics has been falsified. We are left with a profound epistemological puzzle. The mathematics tells us the extra dimensions should exist. The universe refuses to show them. In 1954, a mathematician named Eugenio Calabi announced a conjecture at the International Congress of Mathematicians in Amsterdam. It concerned a special class of geometric spaces called Kähler manifolds. Calabi proposed that under certain conditions, these manifolds would admit a special kind of curvature called Ricci flat curvature. The conjecture was technical, abstract, seemingly far removed from any physical application. Calabi had been born in Milan in 1923. His family was Jewish. His father, a lawyer, quizzed young Eugenio about prime numbers at the dinner table. In 1938, when Eugenio was 15, the family fled Italy under the fascist racial laws. They emigrated to the United States. Calabi enrolled at MIT at 16, studied chemical engineering, was drafted into World War II, served as a translator in France and Germany, and only afterward pivoted to mathematics. He earned his PhD from Princeton in 1950. Under Salomon Bochner, his conjecture was not proven. He proposed it, worked on it, could not complete the proof. The result became known as the Calabi conjecture, one of the major open problems in differential geometry. Xing Tong Yao was born on April 4, 1949, in a village in Hong Kong with no electricity or running water. He was the fifth of 8 children. His father was a professor of philosophy who had fled mainland China. The family was poor, but educated. When Yao was 14, his father died of kidney cancer. The family was plunged into destitution. There was no money for food, let alone education. The boy, who had been a street gang leader, retreated into study. He worked obsessively, using mathematics as escape and purpose. With borrowed money, Yao flew to Berkeley in 1969 to study under Xingshen Chen, the most influential Chinese mathematician of the 20th century. Yao completed his PhD in just 2 years, an almost unheard of speed. In 1973, at a geometry conference, Yao announced that he had found counterexamples disproving the Calabi conjecture. Calabi was in the audience. He listened politely. He said nothing publicly. Months later, Calabi wrote to Yao, asking him to clarify the details of his counterexamples. When Yao sat down to write out the argument rigorously, he discovered that his counterexamples were wrong. The claimed disproof did not work. Yao spent the next 3 years trying to prove the conjecture true instead. He worked, by his own account, to the point of physical exhaustion. The problem consumed him. On Christmas Day, 1976, Yau met with Calabi and Louis Nirenberg at Nirenberg's office at the Courant Institute in New York City. They went through the proof together, line by line, step by step. The proof was correct. Calabi recalled that it was the only time in his life he had a meeting on Christmas Day, and that Yau's proof was his best Christmas gift. Yau won the Fields Medal in 1982. He was the first person of Chinese descent to receive the award. He jokes that he almost believes his first name is Calabi because the two names are so often spoken together. In 1985, Philip Candelas, Gary Horowitz, Andrew Strominger, and Edward Witten published a landmark paper titled Vacuum Configurations for Superstrings. They showed that if string theory is correct, the 6 extra-spatial dimensions must be compactified into a Calabi-Yau manifold. Pure mathematics, developed over 3 decades with no thought of physics, turned out to be exactly what string theory needed. The topology of the Calabi-Yau manifold determines the physics we observe. The number of holes in the manifold determines the number of particle families. 3 holes means 3 generations of fermions, quarks, and leptons, exactly what the standard model requires. The shape parameters, called moduli, determine particle masses and coupling constants. We can calculate what these hidden dimensions look like. We can determine their topology. We can derive particle physics from their geometry. We know all of this about structures we have never seen and may never see. The scale of these hidden dimensions is typically assumed to be near the Planck length, roughly 10 to the negative 35 meters. To put this in perspective, the Planck length is to a proton what a proton is to the distance from Earth to Alpha Centauri. These dimensions are not just small. They are smaller than anything we have ever measured, smaller than anything we can currently conceive of measuring, smaller than the smallest scale at which our current physics makes sense. At every point in the 3-dimensional space you inhabit, there is allegedly a Calabi-Yau manifold, a 6-dimensional geometric structure curled up at a scale 20 orders of magnitude smaller than an atomic nucleus. You pass through trillions of these points every second. You never notice. You cannot notice. The dimensions are there according to the mathematics, but they are inaccessible to any perception or measurement we can currently perform. The irony is profound. We can calculate the exact shape of these hidden dimensions. We can determine their Euler number, their Hodge numbers, their moduli space. We can derive from their geometry the number of particle generations, the structure of the gauge groups, the approximate scale of the cosmological constant. We can do all of this mathematics with complete rigor, and we cannot verify any of it. Calabi died on September 25th, 2023. He was 100 years old. His conjecture, once an abstract problem in pure mathematics, had become the foundation of theoretical physics. When asked about the connection between his work and string theory, he said, "When I first posed the conjecture, it had nothing to do with physics. It was strictly geometry. We find ourselves in A square's position." He was lifted out of his 2-dimensional world. He saw directly what others could not perceive. He returned and described it. He was imprisoned for his testimony. We have not been lifted out. No hypersphere has appeared to explain the 4th spatial direction. We have had no direct experience of the extra dimensions, but mathematics has shown us, with rigorous proof, that higher dimensional spaces are logically coherent, geometrically complete, and in the case of string theory, physically necessary. The equations do not work in 3 spatial dimensions. They do not work in 4 or 5 or 9. They work in 10. This is not a model choice. This is not a philosophical preference. This is the mathematics refusing to function otherwise. And for a century, we have searched for evidence that those dimensions exist in our physical universe. We built the Large Hadron Collider, 13.6 tera-electron-volts, nothing. We built torsion pendulums sensitive to deviations at 52 micrometers, nothing. We studied supernovae and neutron stars for signs of energy leaking into extra dimensions, nothing. The mathematics demands that dimensions exist. The universe refuses to show them. Think about what this means. We have a mathematical framework developed by some of the most brilliant minds in human history that is internally consistent, that unifies gravity and quantum mechanics, that produces extraordinary pure mathematics, that passes every logical test we can devise, and it tells us with the certainty of a mathematical theorem that space-time has 10 dimensions. We have an experimental program funded to the tune of tens of billions of dollars, employing thousands of physicists using the most sophisticated instruments ever constructed, and it tells us with equal certainty that there is no evidence for extra dimensions at any scale we can probe. These 2 facts coexist. The mathematics says the dimensions must be there. The experiments say they are not detectable. Both statements are true. This is not like other scientific controversies. It is not like the debate over dark matter, where we have indirect evidence but cannot directly detect the particles. It is not like the debate over the interpretation of quantum mechanics, where all interpretations make the same predictions. It is something stranger. We have a theory that makes a specific, definite claim about the structure of reality. Reality refuses to confirm or deny it. The parameter space shrinks with each experiment, but never to 0. The dimensions, if they exist, are always just beyond our reach, always at a scale we cannot quite probe. Some physicists find this maddening. Others find it liberating. The mathematics is beautiful. The theory is consistent. Perhaps that is enough. Perhaps we should be grateful that human minds can comprehend such structures at all, even if we can never touch them. Others say this is the end of physics. A theory that cannot be tested is not science. It is philosophy at best, religion at worst. The landscape of 10 to the 500th vacua is not an explanation. It is an abdication. If any universe is possible, then nothing is predicted. If nothing is predicted, then nothing is explained. The debate continues. Careers are built and destroyed. Nobel laureates denounce each other in public, and the universe remains silent. There are 3 possibilities. The dimensions are there, and we are blind to them, genuinely trapped, perceiving shadows on a wall, while the full structure of reality extends beyond our comprehension. We are K² before the sphere arrived, living in a reduced projection of a higher dimensional world, unable even to imagine the direction we cannot see. Or the most beautiful theory in physics, the only known consistent quantum gravity, is completely wrong about physical reality. The mathematics works perfectly. The consistency checks pass. The Fields medals are awarded, and none of it corresponds to our universe. It is a dream within the equations, no more real than Flatland itself. All the dimensions exist at scales we can never probe, at energies we can never reach. The Planck length is 10 to the negative 35th meters. Our best experiments reach 10 to the negative 20 meters. There are 15 orders of magnitude between us and the scale where string theory makes predictions. We may never bridge that gap. We may be stuck forever, knowing the mathematics, unable to test it. The universe refuses to tell us which. Edward Witten once said that the M in M theory could stand for mystery, for murky, for the level of understanding being primitive. Perhaps it stands for mirror, a mirror in which mathematics shows us our own limitations, a higher dimensional structure reflected dimly in equations we can write but cannot test. A square wrote his account from a prison cell. He had been lifted out of his world. He had seen directly what his fellow Flatlanders could not perceive. He returned and described what he had experienced. Nobody believed him. His brother called him a heretic. He wrote anyway, not because anyone would listen, but because he had seen what he had seen. The final line of Flatland reads, "I cannot give you the proof, but repeat those words with me. Upward, not northward. Upward, a direction that does not exist in Flatland. A direction that a square cannot point toward, cannot demonstrate, cannot prove to anyone who has not seen it themselves, but a direction he knows is real because he has been there. We cannot point toward the fourth spatial dimension. We cannot point toward the fifth or the sixth or the 10th. We cannot show you a direction perpendicular to height, width, and depth. We cannot demonstrate the curled Calabi manifolds that allegedly exist at every point in space. We cannot prove to you that the extra dimensions are real. But the mathematics can. The mathematics shows us with the same certainty that proves the existence of irrational numbers, that higher dimensional spaces are coherent, consistent, and in string theory, necessary. The mathematics does not care whether we can perceive these dimensions. The mathematics does not care whether we can test them. The mathematics simply is. And so we find ourselves in a strange position. We are creatures who have proven through rigorous logical deduction that reality may have a structure we cannot experience. We have reasoned our way to knowledge that transcends perception. We have built, out of pure thought, a map of territories we can never visit. Is this triumph or tragedy? Is it the highest achievement of the human mind or its ultimate limitation? We have seen in the equations what Riemann saw in 1854, what Kaluza saw in 1919, what Shirk and Schwartz saw in 1974. We have glimpsed, through mathematics, a reality beyond our senses. And then we built the Large Hadron Collider. We reached for confirmation. We searched for evidence. Nothing. We have the proofs. We have the calculations. We have the shapes of dimensions we cannot enter. And we remain in our cell, writing testimony, waiting for a visitor from outside. One who may never come. Upward, not northward, a direction we cannot point toward, a direction we know exists, a direction we may never see. Perhaps that is the lesson. Perhaps that is what the mathematics has been trying to tell us all along. There are truths that transcend experience. There are structures that exist beyond perception. The human mind, for all its limitations, can reach them through reason alone. Or perhaps we are simply wrong. Perhaps the mathematics, beautiful as it is, describes nothing real. Perhaps Feynman was right, and string theory is crazy, and the extra dimensions are a collective delusion, and some future generation will look back on our equations the way we look back on epicycles. We do not know. We cannot know. We wait.